The ocean in Avatar: The Way of Water cost $400 million to create. James Cameron spent over a decade filming an alien sea full of glowing creatures on a moon called Pandora. But here's the problem no one in the theater questioned. That ocean shouldn't exist. Pandora orbits a gas giant far from its star. It should be frozen solid, dead, a ball of ice in permanent darkness. And yet, NASA just launched a spacecraft to visit a moon exactly like Pandora, because Jupiter's Europa appears to have an ocean, and something in that ocean might be alive. Europa is slightly smaller than our moon. It orbits Jupiter at a distance where sunlight delivers less than 4% of the warmth Earth receives. Surface temperatures hover around -160 degrees Celsius. Ice miles thick encases the entire world. By any normal accounting, Europa should be frozen to its core. But in 1979, the Voyager spacecraft flew past Jupiter's moon Io, Europa's neighbor, and found something impossible. Io was erupting, volcanoes everywhere, more volcanic activity than any world ever observed. Io isn't near any star. It has no obvious heat source. So where was all that energy coming from? The answer had been predicted just weeks before Voyager arrived. Three physicists, Stanton Peele, Patrick Casson, and Ray Reynolds, published a paper making an extraordinary claim. Jupiter's gravity was cooking Io from the inside. They calculated that Io should be volcanically active. Voyager confirmed it almost immediately. The prediction stands as one of the most dramatic in planetary science. The mechanism they identified is called tidal heating, and understanding it requires imagining gravity not as a force that pulls things down, but as a force that stretches things apart. Think about Earth's ocean tides. The moon's gravity pulls harder on the side of Earth facing it than on the far side. This difference, this gradient, creates a stretching force. Ocean water bulges toward the moon on one side and bulges away on the other. Earth rotates beneath these bulges, creating tides. Now imagine the same thing happening to rock, not water, solid rock. That's what happens to Io. Io's orbit around Jupiter isn't perfectly circular. It's slightly elliptical because Europa and another moon, Ganymede, tug on Io periodically, preventing its circularizing. When Io swings closer to Jupiter, the tidal stretching intensifies. When it swings farther away, the stretching relaxes. Io is being squeezed and released, like a rubber ball repeatedly kneaded in a fist. Friction converts that mechanical deformation into heat. Estimates suggest Io generates roughly 100 trillion watts of power by tidal heating, about 6 times humanity's total energy consumption. That's enough to melt rock. Io's interior churns with magma that erupts through the surface in volcanic plumes hundreds of kilometers high. But here's where Europa enters the story. Europa orbits farther from Jupiter than Io, so it experiences weaker tidal forces. Not enough to melt rock, but perhaps, just perhaps, enough to melt ice. In 1998, NASA's Galileo spacecraft measured Europa's magnetic field. The readings were bizarre. Europa generated no magnetic field of its own, but it responded to Jupiter's powerful magnetism in a specific pattern. The pattern expected from a global layer of electrically conductive material beneath the ice. Salt water conducts electricity. A buried ocean would explain the signal perfectly. Subsequent observations strengthened the case. Measurements of Europa's gravitational pull revealed its outer shell flexes by about 30 meters every orbit, far more than solid ice could accommodate without fracturing catastrophically. Something liquid must be absorbing that deformation. The current best estimate, Europa harbors an ocean roughly 60 to 150 kilometers deep, containing perhaps 2 to 3 times the volume of all Earth's oceans combined. Under a shell of ice maybe 15 to 25 kilometers thick, a vast dark sea has likely persisted for billions of years. But Europa isn't alone. Saturn's moon Enceladus, a world only 500 kilometers across, is doing something even more dramatic. It's actively venting its ocean into space. In 2005, the Cassini spacecraft spotted plumes of water ice spraying from cracks near Enceladus's south pole. Subsequent flybys flew directly through those plumes and analyzed their composition. The results were staggering. The geysers contain salt, silica particles consistent with hydrothermal activity, and, critically, molecular hydrogen. On Earth, molecular hydrogen bubbling from hot seafloor vents feeds entire ecosystems that have never seen sunlight. Microbes at the base of these food webs harvest energy from chemical reactions, not photosynthesis. They're called chemotrophs. Some of the oldest life forms on Earth belong to lineages that thrive in precisely these conditions. Enceladus appears to have the ingredients: liquid water, heat, and chemical energy gradients, the three requirements for life as biologists understand it. A tiny frozen moon around Saturn might be habitable. This brings the story to October 2024, when NASA's Europa Clipper launched from Kennedy Space Center. The spacecraft will reach Jupiter in 2030 and conduct dozens of close flybys of Europa, carrying instruments to map the ice shell's thickness, measure the ocean's salinity, and hunt for organic molecules. One instrument, a thermal camera, will search for warm spots that might indicate where ocean water approaches the surface. The mission cannot directly detect life. No instrument can peer through kilometers of ice to find microbes swimming below. But Europa Clipper can determine whether Europa's ocean is habitable, whether the conditions exist for biology to theoretically survive. Here's the uncomfortable truth. We don't know if tidal heating alone can sustain life. Earth's hydrothermal vents benefit from photosynthetic ecosystems that add oxygen and organic carbon to the ocean system. Remove that input, and the chemical energy budget shrinks dramatically. Whether a completely dark ocean, isolated from stellar energy for billions of years, can support anything alive remains genuinely uncertain. Some models suggest Europa's ocean might be too acidic or too alkaline. Others suggest it might be essentially sterile, water and warmth present, but not the right chemistry. The optimistic scenario, Cameron's vision of a teeming alien sea, requires conditions to align in ways we cannot yet verify. But consider what tidal heating implies. Moons around giant planets can maintain liquid water far from any star. The habitable zone, that narrow ring around a sun where temperatures permit surface oceans, might be almost irrelevant. The universe could harbor more ocean worlds as moons than as planets. Exoplanet surveys have found hundreds of gas giants orbiting other stars. Many likely have moons. Even if only a fraction experience significant tidal heating, the number of potential ocean worlds in the galaxy might vastly exceed the number of Earth-like planets orbiting in traditional habitable zones. James Cameron placed his alien ocean on a moon orbiting a gas giant because it looked spectacular, but the physics he borrowed from reality might be the most common setting for life in the cosmos. Not sun-warmed surfaces like Earth, dark, ice-covered seas heated from below by the relentless gravitational kneading of massive worlds. When Europa Clipper reaches Jupiter in 2030 and begins its reconnaissance, humanity will have its first detailed look at such a world. The spacecraft won't find luminescent whale creatures, but it might find something stranger, evidence that the conditions for life exist somewhere we never expected, heated by gravity alone, waiting beneath miles of ice in permanent night. The universe may be full of hidden oceans. The question that remains is whether anything has found a way to swim in them. Like if this was interesting, hit the subscribe for more and turn that notification bell on.